My name is Javion Looney, and this is my physics term project. Today, I will be going over projectile motion. So, as of this point, we should have learned one-dimensional kinematics on objects. So, knowing the horizontal motion of an object in that equation, and then vertical motion of an object in that equation. With this knowledge, you should have been able to recognize different components of the horizontal components and vertical components, as if you threw a rock off a cliff, how high or how long would it take for the rock to hit the ground, and things of that nature. So what is projectile motion? Projectile motion is an object moving along a curved path, both horizontally and vertically, under the influence of gravity. It is represented in a parabolic pathway, and the horizontal and vertical motions of the object are completely independent from each other. So if you were to, we'll see an example later on this, but if you were to drop a ball at free fall and shoot a ball at when they're at the same height and drop, they will both hit the ground at the same time. So no matter the horizontal component of the object, if the balls are released at the same, or released from the same height, they will hit the ground at the same time. This picture on the side here just shows you some of the ways projectile motion works. If you throw it, it'll create a curved pathway. It won't go straight up and down, or it won't create like a sharp maximum height, I could say. So here are some real world applications of projectile motion. We have football. Let's say the quarterback has to calculate in his head how far he has to throw the ball to get to his receiver, how much force he has to use, and things of that nature. What's the velocity that the ball has to have to reach the player he's trying to throw it to. Another example is a cannon. If you wanted to come up with an equation for this situation, you would say, how high should I have to shoot the cannon for it to go over the wall? And what velocity does a cannon need to go to reach over the wall? Another example is a basketball. This is very common in many people's everyday. What X do you need to get the ball from your hands to the goal? How far does it need to go? So we'll go over an example in a minute. Components of projectile motion. We have some of the velocity in the x direction, and yes, in the x in the angular, calculating the angular component of the x. And the y, we have the gravity component, g here, and y's angular component too, and gravity is 9.8. Question as a projectile is fired with an initial speed of 38.8 meters per second at an angle of 42.2 degrees above the horizontal along a flat firing range. Determine the maximum height reached by the projectile. That's the first question, and then we'll get to the second questions in a second. So, first I like to draw it out. So we have the flat range, and then projectile is fired. So we'll just draw an arrow here. At initial speed of 38.8. So we have your velocity your initial velocity at 38.8 meters per second. And it's at an angle of 42.2 degrees. So we can write that as well. The initial angle is 42.2 degrees. And gravity is a constant. That'll be 9.8 meters per second squared. Meters per second squared. So the first question asks us, the maximum height reached by the projectile. So the maximum height we can represent as h. What is h? So h we can represent with the equation initial velocity sine theta squared over 2g. So we just plug in our numbers that we have. We have 38.8. That's the initial velocity, 38.8 sine, and then the initial angle, 42.2. All that squared under 2.98. And we can calculate that. If we calculate that, it'll equal 34.66 meters. So that's just how a quick calculation of calculating the maximum height. And if you notice, we only use the y components. V velocity sine theta, that's your y component for the projectile motion. So B asks us, what is the total time in the air? So for this one, we're looking for a t. Where's your t? T, we can use your y components as well, 2 v sine theta over g. And this is really just about manipulating your equations and your formulas given to you to find whatever components you're looking for. So just plugging in our numbers again, times 38.8 sine 42.2 over 9.8.
Hey, you boss man?
And quick calculation again will give us 5.32. So, seconds, that is. So you're gonna have your seconds. So it takes you 5.32 seconds total time in the air until it hits the ground. So C, next part of the question, C, determine the horizontal distance covered. So in this question, we'll use our x components. And we'll represent that with r. R equals v, the initial v squared g sine double angle theta. Plugging that in again as we have been doing, 38.8 squared over 9.8 times sine 2 times then your angle 42.2. If you get your calculators out and do that math, be equal to 52.88 meters. And that is the total distance covered from your initial point to wherever it lands. And your last question is, what is the speed of the projectile 1.5 seconds after firing? So one more time, we'll take they gave us a t this time, so we'll take that t. Take the t. You want to find for this equation, you're going to use both your x and your y components. So vx, vy, to find the speed. And this is represented with the x, is represented as v cosine theta, and your y is v sine theta. Plug this in, 38.8 cosine 42.2, and then 38.8 sine 42.2. And you get 28.74 meters per second. And, oh, my apologies, I didn't finish the y. For that, you get 28.74 meters per second. And your y, you're going to subtract 9.8, it's gravity, times 1.5, your seconds. So for this is the whole structure of projectile motion, using your x and your y components to get the answer. This will be 11.36 meters per second. But we're not done yet. To find the total component, total speed, use V, and then your x velocity plus your under a root. I'm going to do that really quickly. 28.74 squared plus 11.36 squared. And with a calculator, you'll get 30.9 meters per second. Okay, so if we go back to our slides here, we see that the speed in x, like I said in the beginning, the speed in the x direction is constant, while the y direction of the object moves at a constant acceleration of g, meaning that the balls will be dropped at the same time, as I will show you in this video. So if you look, you see as he drops the ball from free fall on the left, the ball is shot on the right and not on the ground at the same time, showing you that the y components remain constant, or the x remains constant, and the constant acceleration g and y acts the same. So thank you for listening to my lecture. This is Javion Looney once again.